right, can everyone hear me? Perfect. Welcome to United Astronomy Clubs of New Jersey. We are here once again in Jenny Jump State Forest in Hope, New Jersey. Uh, just to give, I saw a few extra people parking, just to give them a little bit of time to come on down, find a nice, either set up their chair, lay down their blanket, find a nice patch of ground to sit on. I do want to welcome not only everyone joining us here, but also online, because that's right, we do live stream these to both YouTube and Twitch. So if you're ever on a Saturday night around 8 p.m. looking for something mildly educational to occupy your time, do feel free to come join us in chat, say hi, ask questions. For people online, if you haven't already, hit those like, follow, subscribe buttons. Shameless plug, it does help us get our programs out there and allows us to continue these programs. In addition, I want to encourage everyone to check us out on our website. It's a great resource for not only finding out what talks are coming up, but also what talks we've had with links to our past talks. But also, it's a great resource for finding out about our member clubs, because that's right, we are an organization made up of other astronomy clubs. And one of the easiest ways to nurture your love of space, science, astronomy is to go find your local club. Not only because ease of access, because it's close to you, but also they're going to have tips and tricks for stargazing that will be most relevant to you. Because let's face it, for those of you who are coming from a more light polluted area, such as New York City, perhaps, or Scranton, very light polluted, my tips and tricks since I've grown up out here in Warren County, New Jersey, aren't as helpful for you guys. So, like I said, do check out our member clubs. In addition, feel free to follow us on our social medias, our Facebook, Instagram, our Discord server, all great places to get in touch with us and ask questions, or even just share your pictures of that neat space thing. I know a couple people were sharing pictures of the solar eclipse that happened on Wednesday. So it looks like we're mostly settled in here. So before we get into our presentation, we're going to have a safety briefing. If anyone needs to use the restroom, that is the porta potty in back. It is big, it is green now. It is illuminated by a red light for ease of finding in the dark. This is a state forest. It does in fact get very dark. So people might need a flashlight to make sure you're not tripping over your own feet. I don't know, sometimes I know I need that, considering I'll be night blind after staring at my screen monitoring chat all night. That being said, do try and keep those flashlights, cell phone lights, what have you, pointed towards the ground, because we don't need to accidentally blind people by showing everyone those neat flashlight rave tricks. However, for those of you who drove in, and I know there are many, please use your headlights, because it is no fun getting run over by a car. And so far, we've had a record of having no one run over by a car here. Let's keep that going. 0 out of 10 experience would not suggest it. So no one needs those medical bills or paperwork. We also have a museum and gift shop area. I will be manning that after the presentation, because as of yet, they will not allow me to break the laws of physics and be in 2 places at once. I heard some boos, so apparently people want more of me, and that is the wrong decision here. One of me is enough. As you may have noticed coming in, for those of you coming in, there are many sheds out there. Each of those sheds has a roll-off roof and has its own telescope. The ones with the roofs rolled back are open and have a volunteer manning them. So once it gets darker, feel free to go up to any of those volunteers and ask what they're viewing. Or I know a number of you were asking about the Perseids. The best way is not through a telescope. That's just find a lovely patch of ground and stare at the sky until you see one. So there's also that option as well. But there are volunteers. Feel free to ask them questions, directions, all of that good stuff. But you're not here to listen to me blabber on for forever. You're here to listen to the presentation, and then after the presentation, ask questions. So we're here to learn about the problem of space trash with Dr. Chirag Skolar. He is a computational plasma physicist working at the New Jersey Institute of Technology. He got his bachelor's degree in mechanical engineering at Boston University and his PhD in aerospace engineering at Virginia Tech. He is interested in all things plasma physics with special focuses on plasma material interactions related to renewable energy nuclear fusion devices, plasma turbulence development in Earth's ionosphere, and improving remote sensing capabilities of non-Maxwellian plasmas. And I'm sure many people have questions about that. If you can't hear, I suggest coming forward. Yeah, unfortunately, that is about as loud as that speaker gets. So if people cannot hear, I suggest you move forward. There is a lovely patch of ground. As long as you're not in this white demarked box, you won't get stepped on by people wandering around. So, like I said, if you are having trouble hearing, do feel free to move forward. We do not bite. That being said, we do have many mosquitoes. Use your bug spray because they do bite. With that, here's Dr. Chirag.
Oh, hey, okay, there we go. Okay.
Okay, if the mic's pointed towards your mouth.
Okay, yeah, there we go. Okay. Thank you very much for the introduction. I'd like to start this talk with asking the audience a few questions. How many people here have seen the movie Gravity? Show of hands. Okay, decent number. How about the movie Elio? No, okay, yeah. For those who haven't seen it, I highly recommend it. It's a very good movie, Pixar movie that just came out last year. If you have seen those movies, you have an idea of what it is I'll be talking about today. One last question I'm going to ask the audience, and this is going to be a very open-ended question, so whatever you feel like is the right answers, feel free to shout it out. In what ways, or like how often do you feel like you interact with our space infrastructure on like your regular everyday life? Shout it out. Yeah, you interact with it? Okay, yeah. Zero? Okay. Every time you use your cell phone. Yeah, these are all good answers. Keep those in mind. So the talk that I'm going to give to you today is titled Waste of Space, the Problem of Space Trash. And I'm going to have my talk in like three different components. So the first part is going to be a brief history of all of our space efforts. The next part is going to be an understanding of what space trash is and why we care about it. And the last part is going to be the research that we're doing in the plasma physics community and myself and some of my colleagues at New Jersey Institute of Technology trying to figure out better ways that we could detect some of this space trash. So first I have here just a few examples. We're going to start in the history of what's going on with space efforts. June 20th, 1944 is the very first time humanity ever launched something into space. During World War II, the Nazis launched a V-2 rocket into space. That was part of the war effort. And a few years later, after the war was over, the Nazis thankfully lost, but some of their scientists made their way both to the Soviet Union and the United States, and that helped kickstart each of their space programs. A very important date in space history, October 4th, 1957. Sputnik 1 becomes the first human-made satellite to get launched into orbit, and that kickstarts the space race in the Cold War. And then both the United States and the Soviet Union are each trying to outdo the other in a myriad of different ways to be the first to achieve something in space. So you've got, example, Yuri Gagarin, first human in space, Valentina Tereshkova, first woman in space. At the bottom over here, I have an image of the Tiros was launched on April 1st, 1960. It was the first weather satellite. So like up until then, we didn't really have like these really cool pictures of hurricanes that are just kind of very commonplace that we have now. July 10th, 1962, the Telstar 1 was launched. That was the first communication satellite, and that was the first commercial satellite. Keep that in mind, just this being the first commercial satellite. It was actually also built in Bell Labs, which I think is right here in New Jersey. And of course, at the end, you've got Neil Armstrong takes the first steps on the moon. So, in the upcoming decades, we realized, okay, the moon was good. Let's keep pushing further. We sent probes and satellites to every planet in the solar system. We launched the Hubble Space Telescope, which revolutionized our understanding of the universe. In November 20th, 1998, the first part of the International Space Station was launched, and it's still being used today to do all sorts of fascinating and really cool and exciting research. We keep going, and we keep interacting with and understanding all the different things in our solar system. We were able to get an asteroid sample, bring it back to Earth. We've looked at comets and landed on a comet. Uh, August 25th, 2012, Voyager 1 enters interstellar space. It's currently the farthest human-made object ever. Fascinating things. We launched the Parker Solar Probe, really cool spacecraft, closest spacecraft to the sun. Fastest, where is it down here? Yeah, fastest human-made object. We've got the James Webb Space Telescope that recently launched. Oh, I say recent, it's been 5 years now. Geez. Uh, really revolutionizing our understanding of astrophysics and really upending a lot of the theories that we've had. So really fascinating work. And I don't have this on this slide here, but earlier this year there was the Artemis 2 mission, farthest human space flight ever made, looping back around the moon to kind of kickstart our return to the moon. So those are really great things, and just for us to understand, just how far we've come in terms of space. But there's a few key things that I want to point out here in this slide over here. And if we look in the top middle here, it might be dark to see, but this was on December 21st, 2015, the first successful landing of the Falcon 9 rocket, which was 11 years ago now. I remember when I first saw this, just like how cool it was that we were able to do something like this. And this has actually been incredibly valuable for space travel because it has really lowered the barrier of entry for us being able to use space. Before this, you would make a rocket that would cost a whole lot of money, time and effort, but primarily money, and you would use it once and that was it. You couldn't use it again. And this actually gives us the ability to reuse rockets and make it so that it's easier for us to get objects up into space. And then SpaceX continued their efforts. May 23rd, 2019 was the first 60 Starlink satellites launched. There's more than 7,000 of them in operation now. And September 16th, 2021, the Inspiration 4 launched. This was the first space flight of private citizens by a private company. And more of that has happened since. So we anticipate this kind of space tourism to increase as we go on. So from all of these things regarding the history of our building up our space infrastructure, I want everyone to kind of understand, like, we, in a sense, we're not in the Star Trek sense, but we've become a spacefaring civilization. We keep launching more and more things every year, and we've been doing this for more than 70 years now. And we've really built up our space infrastructure in ways that whether you realize it or not, you're using it probably every day of your life. We have communication satellites that in many ways power phones, TV, radio, internet, different aspects of that. There's the GPS satellites. Many of us, if not all of us, used GPS to get here today. Right? When was the last time any of us used a map to get anywhere, right? There's satellite imagery if you want to look at images of like if you used Google Earth to look at your house or something, right? That's a satellite that took that image to be able to do that. Science applications, there's so many science applications, I can't list them all, but there's very many different ways we can use satellites to understand what's going on in the universe. There's weather observations, like I said with the hurricane, which really improved our understanding of meteorology. And these are all things that we just use in our everyday life. We see the news on the weather. A lot of that comes from understanding what's going on in satellites. So I have over here a plot showing the number of orbital launches per year. And at the beginning, we can see there's not very much, but we were learning how to use space. We increased a little bit, kind of stayed steady for a few decades, dropped a little bit into the 2000s, and then more recently, it's been kicking back up. And that recent increase has been because of the Falcon 9 allowing us to lowering the barrier of entry to space. And that surge has been due primarily to private corporations. And this is something that I want us to keep in mind as we talk more about about this later. But from this slide, the real key thing that I want to get is we've built up all this infrastructure, and it really just kind of shows the testament to human ingenuity, to human engineering, to be able to do all of this in such a seamless way that we don't even realize in our everyday life that we're using all of this. But humans are also good at something else. And that something else is leaving our trash behind everywhere. These are some classic examples of trash that we have in our current environment that we live in. You've got, like plastic on the beach. You've got your classic turtle stuck in a fishing net. Over here on the top middle, we have these are workers in Indonesia burning a bunch of recycling. Up until recently, a lot of countries in the West would export their recycling to other more impoverished countries that didn't know how to deal with it. And this we think we're getting things recycled, but we don't actually have the ability to properly handle it, so they end up burning it. Thankfully, Indonesia passed a law recently so that they're no longer importing that sort of recycling. And the answer is really just they got to make less things made of plastic. But it's a very difficult problem for us to solve. On the top right over here, that is a plastic bag found at the bottom of the Marianas Trench. That's the deepest part of our oceans, and we've got a plastic bag living over there. On the bottom right here is some ocean currents showing where trash kind of accumulates, called like the Great Pacific Garbage Patch, and these ocean currents called gyres. And I'm being intentionally provocative here with making this analogy. The all this trash that we see here is very bad because it affects not only us, but it also affects the living things that we coexist on this planet with. The trash that exists in space only really affects us because of all the issues that we have with it. If we don't foster a sustainable space environment, then the only people that are losing out on it is going to be us, because future generations may not be able to use space in the way that we use it right now. So here is a map showing all of the known objects in our near-Earth space environment as of August 2024. And I want to point out all these different dots represent a different object, but only a small fraction of these are actual active satellites that are doing something and we're actually using right now. The rest of it is other stuff. Most of these objects are in low Earth orbit, or LEO. So you can see right here, right around Earth, there's a whole bunch of points. Then there's a secondary region that's kind of like a ring. Those are in GEO, or geostationary orbit, or geosynchronous orbit. That's where a lot of our GPS satellites tend to be. That's a useful orbit because I've got a satellite pointed over there, and then 2 hours later it's still over there. So it's very good at understanding position keeping. Now this looks really bad over here, and I'm not saying it's good, but I want us to understand that space is big, and not just from like the cosmos is this unfathomably large thing, right? That is true, but just our near-Earth space environment is big. If we were to actually plot these dots to scale for the actual size that each of these objects are, and I were to show you this, you would say that you wouldn't see anything. You'd be like, oh, there's nothing there. So I want us to keep that in mind. So we have all these objects in there now, and we've realized when we measure these objects over time, here I've got over time looking at the number of objects disaggregated by which orbit that they're in. The majority of them on the bottom we can see are in Leo. This plot and a lot of other plots I'm going to be showing you are from the European Space Agency, the ESA's space debris report. So if you want to learn more about it, I highly recommend Googling that. There's a lot of useful information on there. But we can see over the years that number is increasing. Most of it is all in low Earth orbit. And there's about, by the last point we have here, about 40,000 plus objects that we can see. The orbital launches on the order of hundreds per year, and if we count up all of them up to July 31st, 2025, that number is 7,016. But we see 40,000 plus here, but we think there's actually a lot more than just the 40,000 that we can observe. We have reasons to believe, based on when satellites come back, or objects come back to the ground, and we look at the impact craters, we can get an understanding of like the orbit distribution and the size distribution of particles that might be up there in orbit. So we think there's maybe 54,000 objects greater than 10 centimeters, 1.2 million between 1 to 10 centimeters, and 130 million between a millimeter to a centimeter. So between the 40,000, the 130 million, and only 7,000 launches, how do we square where all of these objects are coming from? And the answer for that lies in several different things. Part of it is, this is the same GIF I showed before with the Starlink satellite launch, is that one launch can shoot multiple objects. So this launch is a single launch, but 60 Starlink satellites were launched from just this one thing. So that's part of it. The other part of it is that you can get parts that broke off of a satellite. So maybe a satellite that was fully functioning is one object, but now if a part of it broke off or something broke with a satellite, now you have two or more different objects that are accounted for. You could also have rocket remnants. This one is probably a Falcon 9 that launched this Starlink satellite, so it probably made its way back down to Earth. But before the advent of the Falcon 9, rockets would launch an object into orbit, and that rocket was also generally in a similar orbit, so it would continue orbiting around the planet for quite some time. So there are still many rocket remnants floating around in space. And the last bit is, chips of paint or leftover propellant going through the atmosphere is a lot of shaking, so we can make a lot of that. And in recent years, I've got a plot here showing the number of payloads launched in low Earth orbit, and you can see it's disaggregated by who made these plots. And we can see commercial entities have just really bumped up the scale, and most of that is Starlink. But Starlink is not the only one to blame. In future years, there's upcoming constellations of satellites that are anticipated by several different companies. So now we have an idea of where some of this debris is coming from, and the question is, why do we care? Why is it bad? I'm painting it in a way that it's bad, and the reason is that objects in orbit move very, very fast, like incredibly fast. So here is a quick calculation that I did. On the y-axis, we have the velocity. On the x-axis, we have altitude. So the blue dashed line is the maximum altitude of LEO. And this is assuming a circular orbit, simplified, but it gets the general idea. In LEO, you're looking at maybe 15 to 17,000 miles per hour that your object is moving. That is incredibly, incredibly fast. Even if you get up to geostationary orbit, you're at maybe 7,500 miles per hour. So really, really, really fast. So, very, very similar to a concept of like a bullet. When you have something really, really fast, even though it's small and moving and hitting something, it can cause a lot of damage, potentially catastrophically. I've got a few examples of this damage over here. On the bottom left is a 1/4-inch hole in the radiator of the Endeavour space shuttle. In the middle, I have an impact crater on the window of the Challenger space shuttle, and this crater was caused by a 0.2 millimeter speck of paint. Incredibly tiny, little tiny speck of paint caused that. And then on the right, we have a hole in the arm of in the International Space Station. This is something that's used for fixing several things on the outside of the space station or doing some sort of experiments. So we have a hole on that. And, thankfully, all of these things here are not super vital objects or they've been, designed in such a way to be able to handle these sorts of impacts. But, what if for this International Space Station bit, what if there was an astronaut there doing some sort of spacewalk, right? That could have turned into something that was a tragedy. So it's very important for us to understand what's going on with space debris, because we want to make sure that, people don't get hurt and the things that we care about and rely on don't get injured or broken. So I have here, I'm about to show a video of the first major debris-causing accidental collision. And accidental is an important word. We'll get back to that later while I'm highlighting accidental. But this is the 2009 Iridium Cosmos crash. Right here is the Iridium satellite, and over here, you'll see it a bit more clearly in a little bit, is the Cosmos satellite. At the time, in 2009, the Iridium satellite was an active communications satellite. I don't know what exactly it was doing, but it was actively working and doing something. The Cosmos satellite was not. So I'm going to play the video now. We can see both of them orbiting the planet, coming around, and in an instant, you went from a working communication satellite to a satellite broken up into so many different pieces. So now these orbital debris objects continue their general trajectories. They're generally on that same orbital path. They keep going around. They're going to come back around to the other side of the planet, and those streams of debris are going to cross into each other again. So maybe as those streams cross into each other, maybe there's a few other additional collisions, creating more sorts of debris objects. So we can clearly see that, if you have something up there, you can create these catastrophic collisions, and you go from something very useful that's working to something that is no longer working. So over time, we actually found that the particles will drift in orbits such that they're covering more orbits. So in 7 days, they're generally following their same orbital plane. As we continue, 30 days, it's spread out a little bit, 60 months. By the time you hit 1 year, those object orbits have shifted to take over most of the planet. Now, uh, at the time, in 2009, these particles accounted for 10% of the total number of tracked objects, which is a humongous amount. And we expect actually that some of them will remain in orbit all the way till 2100. This is a quick plot showing how they're going to decay. But that's about 100 years, 2009 to 2100. That's about 100 years that these things are going to stay up there in space, possibly hitting other things. So it's very important for us to understand the importance of this. And we can see several of these major collision events when we look at the count history. This is the same exact plot I showed earlier, but now instead of being disaggregated by which orbit it's in, this is disaggregated by the object type. So if we look at just the payload part at the very bottom, we can see just a steady increase in payloads, and we can see that there's a Starlink satellite at the bottom over here. That's really causing the increase in our number of payloads. The very first thing that we have here is the Chinese ASAT test in 2007, I believe. The ASAT stands for anti-satellite weapon. So at the time, the Chinese showed that they were able to use this weapon and hit one of their own satellites, and it broke into a bunch of different pieces. So that's this one major debris-causing incident. Then there's the Cosmos Iridium collision that I talked to you about. And in 2021, Russia also showed that it has developed capability for the same sort of thing. And that was actually a very dangerous test because at the time, the debris cloud went through the general region where the International Space Station was, and we weren't sure how it was going to affect the astronauts. So they actually told them to go sit in their escape pods for a little bit because those have more shielding. So thankfully, there wasn't really anything that happened, but it just goes to show how important it is and why it's important for us to be careful with how we use space, because when one person does something, it affects all of us, right? And the last bit I want to point out over here at the very top is that there's this thing for unidentified. There's these improved detection methods that are just objects that probably existed beforehand, but we're just constantly improving our methods of detection. So they probably should be in some of these other bins, but we found them and they were like, oh, we don't know where they came from, so we're just gonna throw them in the unidentified bin. So and there's a few other major collision events, but those are the main ones I wanted to point out. And I point out Russia and China because they're the ones that made the most debris from their things, but they're not the only bad actors here. The United States and India have also demonstrated the ability to do these anti-satellite weapon tests. So when one person does it, we can see just how clearly it might affect all of us, with increasing the debris count. So I want to take this to an analogy of something that we've all heard of for quite some time. We take the analogy of climate change, like with global temperature increase. We do have a point where there might be a point of no return. So this was an idea first posited by Kessler and Pillay in 1978, and it's aptly named the Kessler syndrome. The idea goes like this. Imagine you have one object, some debris object, and it hits a satellite. That satellite breaks. Sucks. Then you get 3 objects from that one satellite. Each of those 3 objects then might hit a satellite each. And those satellites break into 3 objects, and et cetera, et cetera. You can see how we have this chain reaction. So if you have enough density of stuff in orbit around Earth, you might end up with this chain reaction where you're unstable and the objects just keep colliding into each other, and you get more and more and more debris particles. And this is the same sort of physics that gets you to to Saturn's rings or any rings around a planet. And over large astrophysical timescales, you can get this beautiful ring pattern on Saturn, but in our sort of human timescale, what we see is a few more collisions that makes using space a little bit more difficult. And we actually already have unstable orbits. This is a plot from Kessler et al. 2010 using data from 1999, and it shows a few orbits that are already in this unstable regime. And we can see that in these plots down here. It's because these orbits, these collisions are occurring at a rate that happens faster than they would naturally decay back into the planet. So on these plots on the bottom here, there's a blue line on the bottom that indicates if we were to say we're done with space and do no more launches, do nothing else with space, even the stuff that we already have now is going to continue colliding and create more and more debris particles. But if that's not going to be the case, because we know and we've seen that there's going to be more and more space launches because the barrier of entry has decreased, we're going to continue using space. And if we keep going at that rate, we're going to see a lot more debris objects and a lot more number of catastrophic collisions. And this is important because if we get that density, if there's enough stuff out there, you get this impassable layer that we can't really, maybe there's an altitude of orbit that we can't use anymore. Because if you want to use it, you shoot a satellite to there, but if there's all these collisions that are going to happen, that satellite's just going to break. So you can't use it. Maybe we can't even pass through it. Maybe, you try to pass through, there's too many collisions out there, and it's going to break whatever it is that you're going to try to get to a higher orbit. So this is really something that we want to think about so that we can have a sustainable environment so that we can continue using our space infrastructure. Because if we don't, then we might not be able to use it in the way that we have been. Now, I don't want you to panic because this is a very slow process. You can see on the bottom, it takes quite some time. But I want you to panic a little bit because we know how climate change action is going. We've known about climate change since the late 1800s, and here we are in 2026 still talking about it. There's not enough policy action, and private corporations still aren't doing enough to ensure that we have good, clean, renewable energy. So, we have to keep this in mind, especially considering private corporations are the ones that are primarily going to be the ones using space and dominating a lot of the space infrastructure. Now, I mentioned a concept of orbital decay. I want to point out that, contrary to popular belief, space is not actually a vacuum. There are particles in space. There may not be many, but there are. On the right, we have a plot where the y-axis is the altitude, and the x-axis is the neutral number density. So at low altitudes, we have a lot of particles, right? I can move my hands around. We can feel the air that's around us. It's a bunch of particles hitting our hands. As we go up in altitude, there's less and less particles, but there are still particles there. And those particles are sufficient enough for everything to face a drag force that's going to eventually slow it down and cause it to undergo orbital decay. So any active satellites that we have out right now need to have mechanisms that make sure that they stay in a stable orbit, like thrusters or something, to keep them in their orbit every now and then. As a quick example, the numbers vary depending on orbits and several factors, but this gives you a general guideline of how long it takes for an object to decay just naturally depending on where it is in its orbit. So let's say we had something in orbit at 100 kilometers. That's going to come down in 2 hours. If you go to 200 kilometers, that buys you a week. If you go to 500, you get to 2 years. If you go to 600, it gets you to 20, and 800 gets you to 200. So really, a few hundred kilometers makes a huge difference in terms of the density and the orbital drag. And we can see on this plot over here on the left, this is the number of objects re-entering per year. And we can see in recent years, we've had a lot of objects re-enter, which is a good thing because that means there's less objects in our space environment so that we can continue using it. And I'm going to just make a side note here about we need to be especially careful about objects orbiting the moon because Earth at least has an atmosphere that helps kind of mitigate this to some extent. The moon has like no atmosphere. And we want to go back with the Artemis missions, really build moon bases and all this stuff around the moon. If we're not careful about our debris around the moon, there's a much higher chance and much easier for us to achieve some sort of Kessler syndrome on the moon compared to Earth. So, we have all of this this trash that's out there. What do we do about it, right? So there are some guidelines that exist to foster a cleaner and more sustainable space environment set by the Interagency Space Debris Coordination Committee, or the IADC. And a lot of these that I'm going to talk about here, they're going to feel like common sense. But if you don't actually actively think about this when you're designing a space mission, then you're going to possibly not be able to use whatever it is that you want to do properly, or you might be doing things in such a way that it's not conducive for everyone else to continue using space in a safe manner. So it's really important to have these things in mind when you're engineering your space mission. right? Examples are, limit debris during normal operations, avoid explosive breakups. If you have an object in geostationary orbit, make sure you move it to a graveyard orbit for 100 plus years. If you got something in Leo, make sure you bring it back down to the planet safely, or you put it in a path so that by 25 years, it's going to naturally just decay. And if you're going to have something deorbit, wherever it lands, you got to make sure it's not going to hit people or things we care about naturally. And if you design your satellite mission, make sure you do it in such a way that you're going to minimize collisions, right? If you know that there's an object somewhere, don't put your satellite there, right? But you have to take this into account when you're designing these missions. And then if an object does show up, can you perform active avoidance measures to make sure that you don't actually hit that object so that whatever it is that you want your satellite to do can keep doing it? But the problem is the IADC is not a regulatory body. It doesn't have any teeth to it. It doesn't have the ability to impose some sort of penalty to make sure that we are all using space in a nice, safe, sustainable way. So that is something that kind of collectively we need to make sure that there's work on. But really, all this does is that it tells us how do we live in an environment that already has all this debris in it. What do we do if, like ideally, we're already unstable, as I showed in the previous slide. Ideally, what we need to do is we need to remove objects. But that's a very difficult problem from a, not just from a, I'm going to start with a technological standpoint, and the next slide I'll explain why it's a difficult problem from an economic standpoint. But these are just two examples that I'm showing over here, but there's a few other examples that exist out there in the literature. This is an example from the ESA Clear Space 1, expected to launch in 2029. There's a satellite, an inactive satellite that they're going to try to grab with this claw thing. It reminds me of the claw game in the arcade that you could play. Basically take that satellite and figure out, can we either bring it back down to Earth safely or push it in such a way that it'll get to a naturally decaying orbit. Another option is the laser orbital debris removal, or a more fun name, the laser broom, where basically, whether it's on ground or in space, you shoot some sort of object with a laser. And it ablates part of the object to become a plasma, so it changes its momentum just a little bit. And if you keep doing it a few times, eventually you could change its momentum enough such that it ends up in an actively decaying orbit. So these are a few ideas, and there's a few others. But the problem is that space debris, like all pollution, is what's considered a negative economic externality. This is also sometimes called the tragedy of the commons. The basic idea is you can always keep passing the buck along to somebody else. And that somebody else is usually the collective us of society. Right? Like right now, if I wanted to shoot something into space, maybe I don't worry about the space debris that I cause, because right now, I can do whatever I need to do in space. That's the next generation's problem. Well, the next generation, they do that, they say the same thing, that's the next generation's problem, et cetera, et cetera, et cetera. And eventually, we get to a point where it's already too late, right? Now we need to deal with it because it affects me directly, but it's already too late because we should have dealt with it however long ago. Right? This is the same reason why all pollution, trash, climate change, emissions, all of that, it's why it's so hard for us to grapple with, is because it's a negative economic externality. And although all the initial objects that were put into space were by government entities and they do have their fair share of blame, modern day space infrastructure is becoming heavily dominated by private industry. And historically, we know that private industry tends to not care about the environment. So ideally, what we need to do collectively, because when I say the collective us, like none of us over here are the ones that are causing these problems, right? There needs to be actual like policy action or something that could help make sure that our environment up there is being sustainable, much like we need to make sure our environment down here is remaining sustainable. I don't want to be all too doom and gloom, though. There have been some successful attempts. On the right side here, I have the share of compliant objects, of objects that are being deorbited. The payloads have not been so good. They're ranging between 10 to 20% per year. But rocket bodies have been incredibly good at making sure that they deorbit, and part of this is probably due to the Falcon 9 rockets. Right now, SpaceX has an economic incentive to make sure that their rockets come back because they can use them again. So this is one example where it's kind of actually working, but in general, more work needs to be done on the policy section to make sure that we can continue using our space environment. So now I'm going to go to the last portion of my talk, which is going to be on the work that we're doing at NJIT and the broader plasma physics community. And the goal here eventually is going to be we want to remove these objects from orbit. But to remove them, first we have to find them. We have to know where they are before we can remove them, right? So a few ways that we already do this in a very good way is through optical measurements. And right, tonight it's a very beautiful night. You might see some satellites fly by. And when you see a satellite, what you're seeing is the sun's light hits the satellite, reflects back down to Earth, and we can see that with our naked eye, right? The telescopes can do a very similar thing. So this is the Cerro Tololo Inter-American Observatory in Chile, and they can use that, capture the light of a satellite, and then you can, or some whatever object, and you can track that, and now you know what that object's orbit is. You can do a similar sort of thing with radar. Here is the Goldstone radar in California, where you shoot a radio wave, it's going to hit the object and it's going to bounce back, and you're going to get some of that radio wave back to you. And it's much the same way that we can detect like aircraft or missiles. You can detect an object in space, and track its orbit that way. Now this works really well for the larger objects, but we have a hard time truly being able to measure the smaller objects. Right? There's like 100+ million smaller objects out there, and I've showed how a tiny speck of paint can really not destroy, but harm something like the windshield of a space shuttle. So it's very important for us to be able to find these small objects, and that's the work that a lot of us are trying to do right now. So I want to give this analogy of a boat, right? We have to remember that space is not a vacuum. So everything else has been looking at how can we detect the actual boat itself. Well, we have a boat going over the water, and the boat itself, let's say, it's small. Maybe we can't see the boat. But if we can't see the boat, maybe there are other things that we can see about the boat. The wake of the boat is much larger than the boat itself. So maybe we can learn about something about the wake of the boat, that we take this really small object, but if the wake is bigger, maybe that is something that's measurable. So that's what we're going to try to attempt to do here, is see if there's something with the wake. Now, space is not a vacuum, but there's one thing I haven't mentioned, and in the introduction, I was introduced as a plasma physicist. Our upper atmosphere, or the ionosphere, is full of charged particles, where it's an ionized gas. Your regular neutral particles existed, but you imagine now one electron has been stripped from them. So you've got a positively charged ion and a negatively charged electron. This is the same plot with the neutral number density, but now overlaid I have the plasma density on top of it as well. So there's less plasma, but there's enough plasma there for us to try to interact with everything and understand what's going on. So this is where I do all of my research. And in your school classes, you might have learned of plasma as the fourth state of matter. So the question is now, can we understand how the wake of a debris particle behaves when we take into account that we have a plasma? And the really important thing about a plasma compared to a neutral fluid is neutral fluids, really the only wave is a sound wave. So, right, the sound that these debris objects make is way too low that we're not going to be able to detect with it in any way. But with a plasma, plasmas interact with electric and magnetic fields. So they have many, many more different types of waves based on those fluctuations. And maybe that is something that is actually measurable that we can do. Here on the right is a diagram called the CMA diagram based off of the scientists who developed this diagram. You don't need to understand it. I don't even fully understand all the bits of it, but the basic idea is on the y-axis you have the magnetic field, and the x-axis you have the density. And depending on the direction you look at with respect to the magnetic field, you will see all sorts of different types of waves. And this is the thing that's really important, because these are the things that are going to interact with electromagnetic signals that we send out or we can detect, and that could be something that might be able to make it measurable. So here I have a simulation I'm about to show from Idzu et al. 2024. And it's basically you have a metal boat going through an ocean of plasma. I'm going to start it now. And it generates what's called a lower hybrid wave. The name of the wave is irrelevant. The basic idea is you have this small object moving to the right, but we can see this wave structure, and that wave structure is bigger than the object. So the question is, maybe this is something that is measurable. Uh, Now, all the work that I'm showing here is like cutting edge research and very difficult for us to fully understand. We don't fully understand what's going on in the wake of these debris objects yet because there's just so many different aspects of the physics for us to consider. Another paper recently by Ganguly et al. 2025 discovered that there might be something called an ion acoustic soliton that forms. So, damn it. Here, okay, I forgot. Uh, this circle with a dot in it represents the magnetic field. In this case, the magnetic field is coming out of the page. And this is very important for us to talk about because the magnetic field is going to change based on where the object is around Earth. So it's very important for us to understand which plasma waves are occurring. So this is the magnetic field coming out of the page, and this is what we see. Now when we have the magnetic field going to the right, we see kind of a different structure. We see the object is actually in this plot centered at 0, 0, so that's here and here. And we can see that there's actually a wave ahead of the object called a precursor soliton, or an ion acoustic soliton. The importance of this is that solitons are nonlinear, potentially long-lasting waves. So if you have a wave that's long-lasting, maybe that gives us the ability to measure it if it's going to last quite some time. So we can see that the wave generally follows the magnetic field. As long as you have a component of your magnetic field in the direction of your satellite velocity, this could be something that could be measurable. So we see when we're magnetic field is pointing directly to the right, we see it go that way. When it's given a little bit of an angle, we see it move up a little bit. In these simulations that they ran, when the magnetic field is coming out of the page, much like the simulation on the last one, we see these vortical structures develop, which is really interesting. But the problem is the numerical methods that they used here don't allow them to have the object be moving fast enough. This is only moving at Mach 1.1. Realistically, we should expect these to be moving at Mach 5, or 5 times the speed of sound. So, what I'm trying to convey is, the cutting edge side, this is incredibly difficult work, and we each have to make these different assumptions to try to understand what's going on. And we can try to piecemeal a little bit of this together to truly get an idea. Here's a very recent paper by Scales et al. 2026, showing a hybrid model that shows all these intricate wave features, and it adds a little bit that the previous models haven't shown. They improved their debris objects charging model, right? If we have a metal object flowing through an ocean of charged particles, well, we should expect eventually that metal object is going to get charged itself. So if we include some of that self-consistent charging, on the top we see the same exact thing that we saw in that first set of simulations, where just the lower hybrid wave developing. Well, as we increase that charging rate, we go down, we can see these really interesting structures begin to develop, and you can see some of those vortical structures that kind of match what we saw in the previous slide. So really the key point that I'm trying to make here is there's all sorts of intricate features in the wake of a plasma, in the plasma wake of a debris object, that maybe are measurable, maybe are detectable. And even though we don't have a full understanding, because there's still a lot more that we can add to these models here that we're working on, we actually have enough that maybe we can try to make some measurements right now based on what we have an understanding over here. And we've done that. Here's a paper from Bernhardt et al. 2023 that actually measured a Starlink satellite and measured its wake by another satellite. So here's a satellite that we used. It's called Cassiope, which is a satellite that's often used in studying the ionosphere. It moves down into the wake of the Starlink object. And at the bottom, you can see this interesting, big and then comes back down wave structure. Now, this is really important because this is not what natural ambient plasma waves look like. And I'm not going to go into great detail about this plot. This plot basically just says when we look at the actual waves that are the frequencies that are buried in that little signature, that kind of matches the simulations that I showed in the previous two slides, where there's a lot of lower hybrid waves. So, maybe this is a method that we can use to actually measure these small debris objects. And we've used this to measure a few other satellites as well. So now this is great. We're able to actually use this and make some measurements. But the problem is you have to take your satellite and make sure it flies through the wake of something else. And that will happen, but how often will it happen? One thing that we want to be able to do is just kind of be able to do this more as generally as possible. So a lot of the work that I do is looking at incoherent scatter radars, or ISRs. This is a common way that we diagnose plasma in the ionosphere. So here are some of our facilities. There's one in Millstone Hill radar in Massachusetts, the Poker Flat radar in Alaska on the bottom. So when we typically use these to diagnose plasmas, what you do is you shoot a radio wave up into the sky. It's going to bounce off the plasma, come back down, and the power that you get back from that radio wave tells you something about the plasma's characteristics. So you get a feature that looks something like this, and these are based on natural resonances of a plasma, the waves that are just going to be naturally existing in a plasma. This middle long section here, which we use the zoom in plot with this double hump structure, is called the ion line. That's based on the ion acoustic mode, or the ion sound wave. So that's a natural sound wave that occurs in a plasma. This smaller bump next to it is called the gyro line. That's based on the natural electron gyration about the magnetic field. If we go a bit further, we see this larger hump called the plasma line, and that is based on just a very natural frequency that exists in the plasma frequency. So we can see that these returns have peaks at these resonances. So now the question is, if we have a debris object and we shoot some radio waves at it and it comes back, would we see some sort of enhancement that looks different from, like, this is kind of like a regular plasma that's not really doing anything? Would it look different? That's the question that we have. And the answer is probably we're working on it. This is some work done by my colleague William Longley at NJIT, and he did some really interesting theoretical work. Normally, when we look at all these different waves, we make the assumption that the waves don't really interact with each other. This is something that we call linear. And that works a decent amount of the time. But there are times where it doesn't work. For example, in the ionosphere, you could have something called photoelectrons, which are just going to naturally exist because a lot of the ionization happens due to the sun's photons hitting our upper atmosphere. They're going to drive what's called the upper hybrid mode unstable. Again, the names of these waves don't matter. The basic idea is you have a high frequency wave that's talking to a lower frequency ion acoustic wave that's coupling to it, and you can see there's going to be actual change that we need to take into account that's going to affect what the radar's results are going to look like. So in this plot over here, the solid blue line indicates what we would see if we didn't take into account this nonlinear effect. And the dashed line takes into account what we would see if we do count this nonlinear effect. And we can clearly see that depending on the different cases that were run here, some cases it makes a big effect, some cases it does not. And initial findings, and from my work, show that, yeah, we do see some enhancements in the lower hybrid waves, which are the exact waves that we saw in the previous slides. And this was also thanks to some improved methods I did to do these nonlinear calculations. A lot of the work I do is very theoretical and math heavy, so I don't want to bore everyone with a bunch of equations. But yeah, so the key thing is that, we have this ability now, and maybe we have a framework to actually be able to do these sorts of detections. This is still very early on in the research, and there's a long way to go. And the question is, are these waves actually detectable in radars? We're still working on that part of the problem. But once we figure that part out, and if that answer is yes, which we're hoping it is, right? The next thing is, okay, let's use a known debris particle or a known satellite as a test case. Can we measure that? And if we can, do we see it as it keeps orbiting around in the same general consistent area and improve our confidence? And we can make projections about its future trajectory. And once we can do that with things that we know, and we know what it is we're looking for, then we can start looking for debris objects, and maybe we can find a whole bunch. So I talked a lot about, several different aspects of the physics that we do at NJIT, and, what space debris is, why it's a problem, and why we should care about it. So I just want to leave it with this slide over here. So in conclusion, we need to become better stewards of our space environment. We've left many objects in space. They've been colliding with each other, making more and more objects. And again, that we is not any of us in the room, right? Or outside over here. And we've got guidelines that help us deal with it, but we need more teeth to actually be able to, have policy to make sure we can foster that nice, sustainable space environment. Right now, from the scientific community side, we're working to better monitor these objects. We're working to figure out ways that we can actually remove these objects. And, here I just have kind of like a sobering picture from paper by Jenkins et al. 2021. In 1957, there was one lone object orbiting Earth for a few months, and that was Sputnik. In 1992, we have a whole bunch more. In 2015, we have even more. It's been 11 years since that plot, so we have even more now. So I want to leave it with, let us hope that we can continue to have science funding that will allow us to foster our near-Earth space environment so that future generations will be able to benefit from all the amazing advancements and technologies that we just take for granted right now. So with that, thank you for your time, and are there any questions?
All right. Thank you for another great presentation. So, we are going to be getting into a question and answer session. And I need to stand. Yeah, there. Now I have slightly less echo. Before that, I want to go over a few things. Safety briefing, since I know a number of you snuck in after the first one. If anyone needs to use the restroom, that is the porta potty in back. It is big, it is green, it is illuminated by red for ease of finding in the dark. We do have a museum and gift shop area. I will be manning that after question and answer session because I cannot be in two places at once. If you may have noticed, it has now gotten dark. So any flashlights, cell phone lights we might be using to try and get around safely, I ask that you try and do keep those lights pointed toward the ground so we don't accidentally blind people. I know I've seen a couple laser pointers in the background. I do ask a couple reminders. It is actually illegal to point them at planes. So no pointing them at planes. They will find out where we are, and we have, in fact, gotten yelled at in the past by the FAA. Let's avoid that. That being said, also try and make sure we're not pointing any lasers at people. Lasers are not, and eyeballs do not mix. When we go to leave, we are using our headlights. As much as we don't like being blinded by headlights, we much rather be blinded by headlights and you be able to not run people over than to get run over. I've been run over, do not suggest it. That being said, people, do be mindful. It is quite busy. There are a lot of people here. Be mindful of your surroundings. So if you see a car moving, try not to be in front of it. We do have a couple scopes open. I do know a couple volunteers took out random scopes. Do feel free to ask them questions and whatnot. See what they're looking at in the sky. With that, we're going to get into question and answer session now, and that's going to go for people here. You're going to raise your hand and wave it about like you just don't care, and I'm going to bring you the microphone. Because chances are, if you have a question, I'm trying to find a place where I'm not going to get static from that speaker. If you have a question, someone else might have the same or a similar question, but just be too afraid to ask it. And we do like online chat being able to hear the questions. Online chat, you have it easy. You're just going to type it into chat, and I'm going to state it. So we're going to start it off real quick here by the first online question, which was... are there any organizations focused on research for how to remove junk from space?
Yes, there are. I can't tell you the names of those because I don't know much about them. But if I go back to this slide here, I mean, there's two right here. The Clear Space one from the ESA is, obviously working on removing this, and whoever this Phillips et al. 2012 is made a paper looking at this. There are organizations that are working on this problem. It's just the problem is there's no economic incentive to do so right now. So it falls on kind of like the more academic and governmental agencies to try to tackle this problem, and people don't, there's no urgent need in terms of what people feel like to work on this, because there's also at the moment there's no economic gain that can be had from it, sadly.
All right, questions. All right, I see one right over here.
I'm just curious as to what method is being used to estimate the number of objects flying around the Earth at the moment.
Yeah, so the I don't know all of the methods, but I know a few of the methods are like these methods where you can use like you can actively measure some of the larger objects with either telescopes or radars. Another method that they use to kind of get like that like hundreds of millions number is you take if some object is coming back down to the planet and we look at it and we see all these impact craters on it, we can do kind of like a statistical analysis and be like, oh, okay, there's probably these many this size objects and these many that size objects, and this is that kind of the regular orbital trajectory distribution. So that's how we can get an estimate. And it's an estimate, right? We don't know exactly the total number out there, but it's kind of we get an idea of what's out there based on statistics like this.
Right. Another question out here.
Thank you, Doctor. Could you tell me, are objects and satellites generally launched in the same direction so that they orbit in the same manner?
They are launched in many, many different ways, depending on what type of orbit it is that you want to do. So if we have, yeah, so if you have a plot of the planet here, you can have satellites that go polar orbits. You could have satellites that do some sort of inclination orbit, or you could have satellites that go kind of equatorially. But generally, they are going to go into the same general direction. And the reason for that is, there's a reason all of our space launches in the United States happen on the East Coast, either in Florida or Wallops Island in Virginia. The reason for that is if you fly east over the ocean, you actually get to use Earth's rotation to our advantage. So we're already like we don't realize it, but because we're spinning around the planet, we're moving at a fast velocity already, and you need to have some sort of velocity to actually achieve escape velocity to orbit. Well, if you can use the planet's natural rotation to give you a boost, that's why we've set our stuff on the east side. China sets their stuff on the east side of China to do its launches. So because of that, things are generally going to be moving in a eastward direction because it's just easier for us to make those orbits, and there's no reason to make it harder if you don't need to. I'm sure there are things that go in the opposite direction, but like you would need like an actual important use case for it to go in the opposite direction.
All right. Our next online question, which also kind of dovetails nicely into that last one, is how much does space junk factor into launch windows for future space missions?
That's a good question. I don't actually know the answer to that
Because I would
question.
imagine no one wants to send their rocket up and go, oh, look, I just took out.
Yeah, no,
You know.
that's exactly true. I don't. It might. I don't know if we've gotten to the point that it matters that strongly yet. Because remember, like there's a lot of these dots here, but as I said, space is big, so these dots, if we were to draw them to scale, are very, very small. So I don't know if it matters entirely yet, but if it doesn't matter now, soon it will matter, and that needs to be something that people will think about in terms of their mission design. But that's something that we would have to Google to see if that's actually something that we've considered in our current launches.
All right. More questions? Perfect.
So I understand the plasma wake research is still very new, but I was wondering how long does it take for radio waves to reach those plasma wakes, and if there's a significant delay, how accurate is it in actually locating and monitoring the location of the satellites?
That's a very good question. I don't actually know the length of time it would take. It's not gonna be that long because they move at the speed of light, and it's the distance between here to a satellite is a few hundred kilometers. So it's from the perspective of the speed of light, it is not that long. But you are right, and there's going to be a lot of uncertainties when we try to. I'll go to a backup slide. So like this is kind of a typical way that when we look at the spectra, we can make measurements to understand like the temperatures and whatnot based on the shape of the spectrum. This is like a very nice theoretical spectrum. The ones that we actually see from measurement look a bit more jagged and a bit more spotty and have to kind of do best fits to get an understanding. And there are uncertainties associated with that. And we haven't gotten to the point yet where we're actually trying to actively look for these satellites. So I don't know how much the uncertainty is going to affect things. My hope is that we see enhancements that are as large as this, so that even if the uncertainty is high, we have these additional power in the spectra that we can, kind of give us more confidence that the measurement is actually accurate. But the key thing is going to be that if we can make one measurement, then we ideally know the direction that the satellite is orbiting, and we have a very good understanding of Kepler's laws. Kepler figured this out in the 1500s, 1400s. I don't know. I should know my scientific history. But we have a very good understanding of what these laws are. So we know, okay, if we have an object here, it's going to be on this trajectory coming back around. Do we see it again? Coming back around, do we see it again? If not that location, maybe some other location that we know it's going to be in. And if we can make these conjunction measurements, that's also going to improve our statistics. I hope that helps.
Also, another resource, if you have radio specific questions, HAMSCI, HAMSCI, look them up. They deal a lot with ham radio and communications like that. So if you have specifically that type of question, they might be a great organization to hit up to learn more.
Yeah, they're going to be very good at understanding like time lags and delays and all that sort of stuff.
I'm like, wait, I have a good resource. Occasionally I get them. Not as often as I would like. All right, so our next online question, which was, did you guys decide on whether you're doing another event for the lunar eclipse later this month? And the answer is, we haven't yet, because we need to make sure we have enough volunteers to open. This isn't a nonprofit, an entirely volunteer-based organization. So our ability to open for special events is completely dependent on whether we can get the volunteer bodies here to properly staff. As you may have noticed, there are many of you. There are much fewer of us. So, we like to be prepared to handle many people, because it's no fun waiting in line for one scope when there's 100-person deep line. We try not to be like the Dorney Park lines. All right, another question out here. Keep in mind, I am very much like the Jurassic Park T-Rex, so my vision's completely based on movement. Bueller, I hear a lot of the crickets. All right, so our next online question is, how much did the astronauts clench when that hit the Challenger windshield? I know I clench when I just hit a comparatively slow bug moving on the highway speeds.
I don't even know if they would have noticed it between like all the other vibrations and I don't know if it was happening at launch or re-entry, but I assume that's when it was. Maybe it was happening kind of when I was already in orbit.
I think they were just imagining sitting in the seat and like you get that piece of road gravel hitting the windshield right in front of you and like But that is a good question. I don't know that we know the answer for that. I'm sure someone does, but unfortunately not us. Online people, if you have any last minute questions, do get those in. I do like to put that out there because by the time we get to, I'm just giving them a heads up because we're in the future. They're still in the past. So our next question's here.
Thank you. Have any of the private corporations sending things up now taken what seems like a real interest in taking responsibility for what they leave behind? And what does that taking responsibility even look like right now with very little or no regulation going on?
Right. Yes and no. Generally, my understanding is they haven't really done anything, but in a sense, let's go back to this slide. So in a sense, part of it is, the Falcon 9 comes back down, so it made sure that there's been less rocket bodies in space because it already is beneficial for them to do that. The other thing is that the Starlink satellites actually they're only expected to operate, I think, 5 years each, before they're going to come down and re-enter the atmosphere. So that's actually a good thing because the current regulations by the IADC are whatever you have in LEO needs to come down within 25 years. So my guess is, around now we should expect an increase in, percentage of payload compliance because a lot of these satellites are going to start coming back down. So from that front, that has been action that's been done. Which is important because they are trying to make sure that they're keeping the environment safe so that we can keep using it. Whether they realize that's important for them or not is another question. But no one, as far as I'm aware, and I'm not that aware because my work is in plasma physics, so I focus on like the latter part of my talk. But there's not really many groups that are working on how do we actually take things out of the space environment. That's really, I think, like the most important thing. But yeah, to help kind of answer questions, like there's a bit of a yes and no to that.
All right. Any more questions out here? I see another one.
First, I need to apologize because I don't get all the technical terms that you presented. But going back to the model that you were working with the boat and the wake, right? So if I only have one boat and the ensuing wake, it's easy to see. But if we're going to have 100 or 1,000, 10,000 of these guys traveling in the same distance, wouldn't the wake be canceled out somehow?
Yeah, it's a very important question. It's a point that I should have made. So there's a few things I want to say to that. So we've got this wake right here. So like imagine you're on the shore. You have to ask yourself a few questions of, when that wave eventually reaches you, right? How are you so sure that the wave that you see is different from just the ambient waves that naturally exist? Like, how can you differentiate that? So that's one aspect of it. And the other aspect of it is, there's going to be a lot of different particles, and they're all going to have wakes that, if you have like two boats next to each other, you're right, the wakes of those boats might interact and might make it even more complicated. I think for right now, we're still early enough that just making a detection of one wake is really valuable improvement to what we already have the ability to detect. And the other thing is that space is big, so there are a lot of particles, but I don't know how many of those particles wakes are going to be interacting with each other that often. So, so I think the answer to that question is you're 100% right. And at the moment, we're just hoping that that's not too big of a problem. And if it does turn out to be too big of a problem, that's a hurdle we'll look at when we get there, and try to increase the actual understanding of what's going on. First, we need to understand the wake of one thing, and then we'll try to understand the complex interaction when we have the wakes of multiple objects together. But it's a really great question and observation.
All right. Our next online question was, are there bills into various governments to start putting consequences to making space trash?
I maybe, I don't know. I somehow doubt it. I don't think it's the most pressing concern on a lot of things right now.
Yeah. Someone could always propose that to whatever your local government is. Because I know sometimes we get people who watch from different countries even, and I know some about the U.S. government structure, but I definitely could not tell you anything about foreign government structure. So you could check that out yourself.
That is an important point. Like this is something that all of us collectively, like on the planet, need to address because one person's actions affect all of us.
All right. All right. Okay. Sorry. I thought you were pointing behind me. I'm like, is there someone behind me?
Segueing off of this gentleman's question,
Yeah.
what is the size of the width? What is the width of these wakes? Are you looking at? How do they What kind of range are we talking about?
Yeah, so here's a plot that I hadn't shown. So here's an example simulation. This is kind of a simplified version, but if we focus on this one over here, our x-axis over here is in meters, so that's like 20 meters across. Our y-axis is in kilometers. So on one side it's not very large, but on the other side it's fairly large. We've taken like I think it's a 25 centimeter object, and we can increase the footprint to like meter scale or kilometer scale depending on which way we're looking at it. So large enough that hopefully we're able to make that sort of measurement very nicely.
All right. So I looks like we're done with online questions. One last question here. Well, he will be around just a little bit while he's breaking down his stuff. So if you have a question that you weren't quite brave enough to say in front of everyone, he'll be around for a few minutes while he's packing up. I do want to thank you once again for coming out and giving another great presentation. I also want to thank everyone who has joined us here and online and supported us just by being here. And an extra thank you to those who have supported us, gone above and beyond and supported us monetarily. It does help us pay the bills and keep offering these free public programs. Like I said, we are a nonprofit organization. We also do currently have a fundraiser going to break ground and build a new observatory shed for our 25-inch telescope that was donated. So your donations go a long way to helping us in this last little bit while we're waiting on permits before we break ground, because oddly enough, we don't want to deal with fines for doing stuff without a permit. They get expensive. But thank you, everyone. Thank you.
Hey,
Like I said, check us out on our website, uacnj.org, for many, much more informations. If you think of a question later, we do save these presentations on YouTube, so do feel free to ask them in the YouTube comments. I do go through them periodically to see if there's anything I do need to answer. With that, have a great night, everyone. Like I said, we have volunteers with scopes open. I'll be in the little museum and gift shop area. And with that, everyone, clear skies and good seeing.